Continuing into part 5 of chapter 21, we're going to look at something called a conjugate addition reaction. So what's going to be important is that we are starting with an alpha-beta unsaturated carbonyl. So let me actually draw an alpha-beta unsaturated carbonyl. So something like this, where there's a double bond between the alpha and beta carbons. That is the product of the aldol condensation, so you could see how it could be linked in to a broader synthesis. But we're going to focus on this position right here. We've been adding to the alpha position, and so we're going to look at an example of how we might manipulate or add to the beta position. It's got some interesting chemistry because of resonance. We already know that the carbonyl carbon is electrophilic, right? It's directly attached to oxygen. That's very electron withdrawing. And so you do have that partial positive, full formal positive charge on this resonance structure. But because it's allylic, you also get a partial positive here at the beta position as well. All right, so that's going to attract a certain type of nucleophile. It's a very specific type. Right? Now, let's take a look at two different reactions that both add an R group. We're going to look at Grainyard and we're going to look at a Gillman reaction. Now, Grainyard is not surprising here. It doesn't do anything that you don't expect it to. All right, so if I'm starting with an aldehyde and I bring in a Grainyard, I work it up with water or H3O plus, something with some protons, then I'm going to get exactly what I expect. I'm going to get an alcohol, and I'm going to add an R group. That is because your Grainyard is a strong nucleophile, and that strong nucleophile is going to attack that carbonyl. But some weaker specific nucleophiles, like Gillman, right, don't attack the carbonyl carbon. What we're going to see here is, let's draw it. In our first step, we're going to use the Gillman. Remember, it's two R groups, CuLi. This one also needs to be worked up. You are going to add the R group to the beta position. And you do lose the double bond. But you keep the carbonyl intact. So let's take a look at that mechanism, shall we? It's on the next slide here. So again, you know that, and I'm going to use the Gillman. There's two R groups, and one of them is going to act as our nucleophile and attack that beta position where we know there is a partial positive charge. We can't have 5 bonds on carbon, so we are going to shift the electrons around, push them out onto the oxygen. That's going to form our enolate. All right, so we've added R, or whatever nucleophile we're adding here. We've got a double bond and then an O minus. So we have our enolate intermediate. Now, when you add your H3O plus, it is going to protonate. But as we've seen in multiple instances, an enol is not always or often not the stable product, and so it is going to tautomerize. We have done the tautomerization mechanism at least twice, once in OChem 1 and once when we, in the last chapter, not the last chapter, earlier in this chapter. And so I'm going to just skip that for now, but you are going to tautomerize, right? Something you already know how to do. Now, Gillman reagents aren't the only ones that can do this. What this is called is a Michael reaction, these conjugate addition reactions. And it's important that you have a Michael acceptor That's the one with the beta position that you're interested in. And then the Michael donor, the one that is going to be giving the electron. So that's your nucleophile. And certain chemicals, certain functional groups will fall into these categories. I want to make the list and then we'll go back. So our donors are Gillman, and then all of the other donors have something in common. For the most part, we're dealing with a distabilized enolate. Now, what's coming off either side doesn't matter as much. You don't want a carboxylic acid, but you could have a ketone, an ester and a ketone. You could even have a nitrile. Remember, nitriles behave very similarly to other carboxylic acid derivatives. Esters and ketones and aldehydes work the best because the carbonyl carbon isn't as reactive as, say, like an acid halide. So off to the sides, right here and here, you could have a hydrogen, you could have an R group, you could have an OR group. You could also have a nitrile, right? It just gives you another place for stabilization. You also could have a nitro group. You're not going to see that one from me. Your acceptors, it looks like a big list, but look at this. They're all alpha beta unsaturated carbonyls. In this case, you can have aldehydes. You can have ketones, esters, amides. You can even have nitriles, right? So anything can really go in here except for a carboxylic acid. It can be HROR, NH2, or the whole thing could just be a nitrile. Again, you're not going to see the NO2 option from me. So let's talk about how these donors and acceptors would behave together. Something that you should notice is the donor is the enolate. So this needs to be deprotonated to react. So that's why in these slides over here, you're seeing something like this Michael donor being treated first with KOH. That is going to deprotonate. We can use the hydroxide. There's nothing there to hydrolyze like an ester. So KOH is fine. I'm sorry I keep yawning. We're going to get through it. And then in number 2, that's when you bring in the Michael acceptor. You bring in some sort of alpha beta unsaturated ketone or aldehyde. We'll go ahead and use what they're using in the slide. 3 is important because even once this is added, you're still going to have a real acidic proton around. So, for instance, here, the product, go down like this. Nothing happens to these guys. We're attaching to the beta position. So if this is 1, 2, 3, 4, it's attaching to carbon 3. So you have carbon 4, 3, 2, 1. You want to keep track of those carbons as always. So you notice you have to pay attention to functional groups, not necessarily what's on the left, what's on the arrow. When we did Gillman, right, we put Gillman on the arrow and we put the Michael acceptor out in front. That's just not always the case. In this particular reaction, we're putting this one down first because we need to add that KOH. We need to prepare it. We need to pull off one of those hydrogens right there. This is the same reaction. Okay. Now, you don't need to know. I'm not going to ask you this mechanism because it's an acid-base step. It is the mechanism that we saw with Gillman, and then it's a protonation at the end. It's all things that we've worked on before. So you need to practice. You need to get to where you can recognize a Michael donor and a Michael acceptor. I know there's some practice up online. Sapling has some practice. Make sure that you feel good about this list. Now, something that you might notice here, these are all dicarbonyl compounds, except for these two. Well, okay, in Gillman. Is there a way that we could add a ketone to the beta position of a Michael acceptor? And the answer is yes, but you have to manipulate it quite a bit. So this next reaction is called Stork enamine synthesis. Now, this is another one. I'm not going to ask you to do the mechanism because it's about 3 different reactions altogether that you do know the mechanisms for. But I do want you to be able to predict products or to use it in a synthesis. So from here, we're going to start with the ketone. They're using cyclohexanone. I'm going to use acetone. And you're going to start by making an enamine. So step 1. Step 1, you're taking your secondary amine, a little bit of acid, and you are making that enamine that we saw in chapter 19. As it turns out, the Stork enamine is actually a good Michael donor. So from here, we're going to add in a Michael acceptor. All right, and I'm just going to do a simple Michael acceptor. It doesn't really matter. Here we go. Now, what's important to recognize? What is actually doing the attacking? You are getting the attack from the double bond to the beta position. And then you're just having this whole flow of electrons out. So you have your enamine here. The ene is gone. You've got this little iminium ion. You have 1, 2, 3, 4, 5, 6. 3 and 4 are now attached. 4 is also attached to 5, and then 6 has that oxygen. Now, when you do your final step and you're going to work this up in acid, 2 things are going to happen. You are going to get your tautomerization, so you are going to get your carbonyl back, right? Your enol and enolate is going to go away. But what happens when you add acid and water to an imine or an enamine? It is going to hydrolyze back to its carbonyl state. So you wind up with Stork enamine synthesis getting a carbonyl 1, 2, 3, 4, 5 carbons apart. Now, this is often written all as one piece, right? So if we wanted to show that reaction instead of in individual steps, put it all together, you are going to bring in that secondary amine. Again, that's what forms your enamine. Number 2, you are going to bring in your Michael acceptor, and then you're going to work it up. You don't have to go through the mechanism to predict products as long as you pay attention to how many carbons you have, right? 1, 2, 3. 3 is attacking this guy right here. 4, 5, 6, 7 this time. So we have 1, 2, 3, 4, 5, 6, 7. And on 6, we have a carbonyl. You are not responsible for Robinson annulation. So you can know Robinson. What it is, it's a intermolecular Michael addition. For intramolecular problems, I'm going to stick with aldol and clays and condensations. So no Robinson annulation. So we'll keep going. And this brings us to the end of the chapter. I really encourage you to look at the synthesis strategies on the the slides or in the book, or if you have the second language book. The there's a lot here. We've got new options for making carbon-carbon bonds. We're organic chemists, so that's so very exciting. But again, that's all kind of for you. Review, lots of little diagrams, stuff to help you study. I definitely recommend it. Your toolbox is huge, right? So that is the end of chapter 21. In the next video that I put up, we will start chapter 22. We aren't doing all of chapter 22, so I know chapter 21 is a beast. Not telling you not to worry, but to ease your fears that 22 would be just as bad, it's not. It's going to be much shorter. So I will see you.